Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes on coordination chemistry, magnetochemistry of coordination compounds. In previous class, explained about the introduction to coordination compounds, then types of ligands, transition metal that D block and F block elements, types of magnetic behavior, orbital contribution to magnetic moment. And this class, I'm explaining about spin orbital coupling. So in previous class explained about how to calculate the spin only magnetic moment. Mu s is equal to root of n into n plus 2 Bohr magneton. So this table represents the listed the octahedral complexes. For octahedral complexes, the spin only calculated spin only magnetic moment value as well as the observed magnetic moment value. So you can see that the spin only magnetic moment values and the observed magnetic moment values are not the same exactly, and some certain cases like a cobalt 2 complex with a high spin, we can see the spin only calculated value is 3.88, whereas the observed value is very high, 4.3 to 5.2. In case of tetrahedral complexes also, the values are given here, the spin only calculated value as well as the observed calculated observed values. Okay, here also you can see in case of cobalt 2 D7, that is E4 T23 configuration, the spin only value is 3.88, and whereas the observed value is 4.2 to 4.8. So why this happened? Why this happened? Why the observed value is higher than the spin only calculated value? Means not only spin only spin angular momentum is considered, orbital contribution as well as spin orbital coupling or spin orbital contribution is also considered. So the extended values of magnetic moments of a large number of complexes are not agreeing with the spin only magnetic moment. Even in the case of when we are expecting there's no orbital contribution, the observed magnetic moment values are generally higher in some cases or slightly lower than the spin only value. So this deviation, it can be explained with the spin orbital coupling. So spin orbital coupling is considered to calculate the effective magnetic moment. Mu effective is equal to mu s multiplied by 1 minus alpha lambda divided by delta, where mu s is the spin only magnetic moment, alpha is the constant which depends upon the spectroscopic ground states, lambda, it is related to spin orbital coupling constant, so it is the spin orbital coupling constant, and delta is the energy difference between the ground state and excited state that we explained with octahedral complexes as delta O and for tetrahedral complexes as delta T. So to understand more about this spin orbital coupling, or how mu effective calculated compared to mu s, and what is alpha contribution of delta, lambda as well as delta, we need to discuss some of the basics based on the spectroscopic ground states. Then the term representation, and that I'll discuss in not in detail, brief. So spectroscopic ground state, in order to explain the spectral transition of metals and their complexes, only the electronic configuration is not sufficient. Different types of electronic interactions such as spin-spin, orbital-orbital, spin-orbital are also need to consider. Okay, that is to explain the spectral behavior of transition metals. Only with the ground state electronic configuration what we write, that is not sufficient to explain that. Therefore, we need to consider the spin-spin, orbital-orbital as well as spin-orbital contributions we need to consider. So this can be categorized by some special symbols called term symbols. Various overall arrangement of electron cloud around the nucleus for a particular configuration is not same as far as the energy or angular momentum are considered. Okay, we explained that electron cloud is there surrounding the nucleus. That is not sufficient. We need to calculate the energy, angular momentum also we need to consider. So these different electronic arrangements can be classified on basis of overall spin, orbital or total angular momentum we need to consider. So the term microstate, it may be defined as the overall electronic arrangements of a particular electronic configuration, which can be differentiated in terms of energy or angular momentum. Okay, if we take the examples, it will be more clear to you. The two types of electronic configurations, they are the when unpaired electrons are present in same subshell, or when unpaired electrons are present in different subshells. Okay, to which how we calculate the microstate, that I will explain in the coming slides. So So microstates we will come to know in detail what are the microstates. So when unpaired electrons are present in same subshell, that is only one subshell is there. There is no combination of PP or DD or PD contributions. We are not discussing. Only unpaired electrons are present in same subshell. That example with the P1 configuration, that is one electron in P subshell. A total of 6 number of ways you can arrange the microstate, or there are 6 number of microstates, 6 number of ways we can arrange the electron. The first one, that one electron only in px with a up spin, or second possibility, electron is present only in px subshell with a lower spin or down spin. A third possibility, the electron is present in py subshell with up spin, then with a low spin, down spin, then pz with up spin, and pz with low down spin. So these are the 6 number of ways, or we call it as the microstates. Now it is clear what is microstate. In case of P2 configuration, if 2 electrons are there in P subshell, then like this 15 possibilities are there, or 15 microstates are there. However, the calculation of number of ways the electrons are arranged in D and F. So with the case of P1 and P2, it is easy. 6 to 15 we can write, and we can check the how the microstates are there, or how the number of ways we can arrange. Whereas if when it comes to D and F with more number of electrons, say D4 or D5 or F6 and all, there are very large number of microstates are there, or very large ways we can arrange the electrons. Therefore, with that particular what we draw previously just now, it is not possible, it is difficult, and we may do error also. Therefore, to calculate the number of microstates, we have an expression or equation. It is n factorial divided by r factorial multiplied by n minus r factorial. Okay, only n factorial is in the numerator, remaining r n minus r factorials are in the denominator. Where n is the twice the number of orbitals present in the subshell. Suppose if p subshell, p has got 3 subshells, therefore n is twice the number, it becomes 6. Okay, and r is the number of unpaired electrons present in them. If only one electron is there, that is only one unpaired electron is there. Like that, we need to find out what is n as well as r. So if you take the example, in case of P1 configuration, that is one electron in P subshell, n is equal to 3 into 2, because P has got 3 subshells, it is twice the value. N is the twice the value of the subshells. Therefore, 3 into 2, it becomes 6. And only one electron is there, therefore r is equal to 1. Therefore, number of microstates are 6 factorial divided by 1 factorial multiplied by 6 minus 1 factorial. Okay, how to calculate the factorial? 6 factorial means 6 into 5 into 4 into 3 into 2 into 1. Like that, 6 minus 1 means that is 5. 5 factorial is 5 into 4 into 3 into 2 into 1. Therefore, if you do the mathematical calculation, you get 6 microstates. For P2 configuration, n is equal to 6, okay, 3 into 2, and r is equal to 2, because it is given 2 electrons are there. Okay, therefore the number of P is equal to 2 means only 2 electrons are there. 2 electrons will be unpaired. Pxo or Py or Px or Pz or Px or Py or Pz. Like that, only 2 that possibility if we calculate, we can say that r is equal to 2. Therefore, number of microstates will be 6 factorial divided by 2 factorial multiplied by 6 minus 2 factorial. That will be 15 microstates, or 15 number of ways we can arrange the electrons. For D2 configuration, n is equal to 5 into 2. So d orbital has got 5 subshells. So 5 into 2, twice the number of the subshells. So it becomes 10. R equal to 2. Therefore, number of microstates is 10 factorial divided by 2 factorial into 10 minus 2 factorial. 45 microstates are there. So like that, if you calculate, you can say that for P1 6, P2 15, P3 20, P4 15, P5 6, P6 1, D1 10, D2 45, D3 like that, D10 it is 1. So the remaining values you can pause the video and you can take a snapshot and you can note it down. Okay, so here we can observe that the same number of unpaired electrons, say P1 has got 6 microstates. Similarly, P5 the same number of unpaired electrons are there. If you write the electronic configuration, we can check the number of unpaired electrons, not the total number of electrons, how many unpaired electrons are there. Therefore we can say that if for same number of unpaired electrons, the number of microstates, the number of ways the electrons arranged can be, it will be the same. Okay, you can check the other examples also. So P215 and P415, like that you can cross check what are the other possibilities in this. Yeah, when unpaired electrons are present in two different subshells, okay, not in the same subshell, two different subshells. Say for that such cases, we can calculate the number of states as n factorial divided by r factorial and n minus r factorial multiplied by m factorial divided by s factorial into m minus s factorial. Here, just like n and r, m and r also this almost the same. M is the twice the number of orbitals present in the second subshell. N is the twice the number of orbitals present in the first subshell, and r is the number of unpaired electrons. S is also the number of unpaired electrons present, okay, in the first subshell or the second subshell. Okay, so if you calculate the values, I'm not doing the calculation, just given listed the values for P1 contribution, electronic configuration. Number of microstate is 36, like that P1 P2, and so on. To P2 D3 it becomes 1800 microstate. For D2 D3 there are 5400 microstates are there, so it is not possible for us to write and check. Therefore we need to use the expression to calculate the number of microstates. The atomic term symbol, the number of microstates in a particular configuration can be distributed in various electronic states represented by atomic term symbol. Atomic term symbol may be defined as the symbolic representation of various electronic states having different resultant angular moments resulting from spin-spin, orbital-orbital or spin-orbital interactions. Okay, now we'll use the word resultant angular momentum or resultant orbital contribution or resultant spin contribution. So the transition between two different atomic states may also be represented using their term symbols, to which certain rules are applied. Okay, so we can write the atomic term symbol as a L with a 2s plus 1 and J. Okay, this is a subscript, this is superscript. 2s plus 1 is a superscript and J is a subscript. 2s plus 1 is towards the left side of that L and J is towards the right side. Okay, where 2s plus 1, that is called as spin multiplicity, and S is the resultant spin angular momentum quantum number, L is the resultant orbital angular quantum number, and J is the resultant total angular momentum quantum numbers. Okay, so just like the case of atomic orbitals, where the small letter L represents the individual orbital angular moments, and L represents the resultant or total or contribution of all that L values. So L is represents the resultant orbital angular momentum of an electronic state and gives the base designation of any atomic symbol. So how we calculate? If L value it is 0, then the corresponding state we have to write as S. That means in place of L we have to write S if the resultant angular momentum, resultant orbital angular momentum value L is 0. Like that, for 1 we write P, 2 we write D, 3 write F, 4 we write G, 5 we write H, for 6 we write I, and for 7 we write K, and so on. Okay, so for orbital coupling, okay, our main topic is spin orbital coupling. So we are discussing the other possibilities. The orbital coupling, for example, small letter L1, L is equal to 1 and L2 is equal to 1. That is two orbitals are joined, combined state we are explaining. So L1 is equal to 1, L2 equal to 1. The 9 different combination of orbital angular momentum can be calculated. As L1, we know L1, 1 means it can have plus 1, 0 and minus 1 possibilities. Therefore, all the combination of L1 and L2, when they come together, their contribution. So plus 1 and plus 1, the total resultant moment will be plus 2. Plus 1, 0, it becomes plus 1, plus 1 minus 1, 0. So on, it is calculated for all the remaining contributions of 9 different combinations are possible. So if this is, we can write, so since it is 1 and 1, we can write the possibilities plus 1, 0 and minus 1. If it is a higher values, okay, for which the mechanically allowed states, we calculate as plus 2 plus 1 0 minus 1 minus 2 plus 1 0 minus 1 and 0, that is 2 1 0. So these are the L possibilities, and the corresponding states what we write. For 2 we write it as D, for 1 we write it as P, and for 0 we write it as S. Okay, so hence the quantum mechanically allowed series can be calculated. So what I said, so if it is 1, we can just write 1 3 times plus 1, 3 times 0, then 3 times minus 1, and then plus 1 0 minus 1 plus 1 0 minus 1 plus 1 0 minus 1, like that we can write, and we can check what is the L value, and we can find out what is the possible, or what are the simple, or the state how we represent. If the values are higher, then it is difficult for us to write this one. Therefore we use the common quantum mechanical allowed series can be calculated with this as L1 plus L2, L1 plus L2 minus 1 till L1 plus L2 minus 2, like that modulus of L1 minus L2, and this value should be a positive value or including 0. That means if L1 is 1, L2 is 1, then 1 minus 1 0 case, you have to stop this. Therefore we'll get 2 1 0. So then writing this table, a table like representation, we can even calculate the quantum mechanically allowed series. So here also we are getting 2 1 0. Therefore it is D, P and S. If it is L equal to 2 and L2 is equal to 2, without writing that table form, how we calculate, it will be 2 plus 2, 2 plus 2 minus 1, 2 plus 2 minus 2, 2 plus 2 minus 3, and 2 minus 2. Therefore it becomes 4 3 2 1 0. That means if L1 is equal to 2, L2 is equal to, we start with 2 plus 2, that is 4, and end with 0. Therefore 4 0 in between 3 2 1 also will come. Therefore now it is easy for us to calculate without writing this one also. We can write it down. So it will be 4 3 2 1 0. If L is equal to 2, L1 is equal to 2, L2 is equal to 2, it becomes 2 plus 2, that is 4. We start with the 4 and we'll end with the 0. Therefore 4 3 2 1 0. And the possible states are, if it is 4, that is G F D P S. For 4 3 2 1 0, the states are represented as G F D P and S. For spin-spin coupling, as previous one we've seen that orbital-orbital coupling. This is spin-spin coupling, that is resultant spin angular momentum, how to calculate. That is calculated as in the same similar way. S is equal to S1 plus S2, where S1 is the spin contribution of 1, and this is the spin contribution of the second one. Okay, therefore S1 plus S2, S1 plus S2 minus 1, S1 plus S2 minus 2, like that, so on, till we get a positive value. Okay, that is represented by this modulus S1 minus S2. For example, T1 P1 or D1 D1 configuration, in which there are only one electron is present, and its spin will be half. Okay, so for S1 is half, S2 is also half, since it is P1 and P1 or D1 and D1, S1 and S2 becomes half. The spin values we represent as half spin. Therefore S can be calculated as half plus half, half minus half, that 1 0. Okay, which means that the multiplicity. So here 2s plus 1, in which s is the 2s plus 1 is the spin multiplicity. 2s plus 1 is equal to 3 and 1. Okay, the multiplicity actually represents the number of orientation possible for the total spin related to the total angular momentum L. The spin-spin coupling for different unpaired electrons are given in this table. If the unpaired electron is 0, then there is no spin present, it is 0. Spin multiplicity we calculate as 2 into S. So 2 into 0 plus 1, it becomes 1. Then we call it as the state as a singlet state in case of spin-spin coupling. If unpaired electron is 1, then it becomes a doublet. If unpaired electron is 2, it becomes a triplet. If it is 3, that is quadret, means the spin multiplicity value we are getting as 4, therefore it is quartet. And if it is unpaired electron is 4, then spin multiplicity value calculated is 5, then we call it as quintet. Like that we can calculate the state in case of spin-spin coupling. So the angular momentum J, due to the interaction of resultant orbital angular momentum L and resultant spin angular momentum S, can be calculated as J is equal to L plus S, L plus S minus 1, L plus S minus 2 till the modulus of L minus S is calculated, becomes a positive value. Okay, therefore calculate state. Say a state is given S3. S3 state is given means here L is equal to 0. 2s plus 1 value is 3. L equal to 0 because it is given as S. S means that is L state is 0. And 2s plus 1, that is left side of that L, 2s plus 1, that value is given as 3. Therefore 2s plus 1 is 3. Therefore if we calculate S here, S is equal to 1. The J value we calculate as L plus S minus 1. In that base we write. So here it is 0 and 1 it is there. Therefore 0 plus 1, that is 1. 0 minus 1 becomes negative value. That is not possible. You have to take the modulus. Therefore J value is equal to 1. Therefore after the spin orbital coupling, or we call it as LS coupling, spin orbital coupling, we write the state as 3s1. Similarly, for other 4, 5 examples I took to explain the spin orbital coupling concept. So for a state P3, P means that is L equal to 1. 3 means 2s plus 1. 2s plus 1 is equal to 3. Therefore, L equal to 1, S is equal to 1. J values are calculated as 1 plus 1, 1 plus 1 minus 1, 1 minus 1. Therefore, it is 2, 1, 0. Okay. Therefore, 1 and 1 are there. Therefore, 1 minus 1, that is 0 is possible. Therefore 2, 1 and 0 are the J values. Therefore the corresponding state after the spin orbital coupling is 3p2, 3p1 and 3p0. Here 2, 1 and 0 is the J values, 2, 1 and 0. 3 is the 2s plus 1 value, that is spin multiplicity value. For D3 state, L value is 2, S value is 1, J value is 3, 2 and 1. Therefore, possible the state after spin orbital coupling are 3D3, 3D2 and 3D1. For S1 state, L is 0, S is 0, J is 0. Therefore, the state after LS coupling we write as 1S0. For P1, the state after LS coupling we write as 1P1. For D1, the state after LS coupling we write as 1D2. The remaining values you can pause the video or you can take the snapshot and you can check it out. Okay, so for D1 electron or D1 system, we can say the possible L values we write as 2, 1, 0, minus and minus 1 and minus 2. So electron is present in only one electron is present. Therefore, the resultant orbital angular momentum L can be calculated as 2 into 1, that is 2. S value, only one electron is there, therefore only half spin is considered. Therefore 2s plus 1 we can calculate as 2 into half plus 1. 2 into half plus 1, the value is 2. Therefore the ground term we write as D2 because L is equal to 2. L is equal to 2, therefore it is represented as the D. And 2s plus 1 value we got as 2. Therefore it is 2D. For D2 system, 2 electrons are there. Therefore, L contribution we calculate as 2 into 1 plus 1 into 1. Therefore, it becomes 3. S value, 2 spins are there, half each. Therefore, half plus half, it becomes 1. 2s plus 1 value, that is 2 into 1 plus 1, that is 2 plus 1, 3. Therefore, the ground term we write as F 3F. The F because L value is 3. For 3, the state we write as F. Therefore, it becomes 3F. Like that, D3 system, the ground term, it becomes 4F. You can pause the video and check it out how it came. For D4, it becomes the ground term we write as 5D. For D5, we write as 6. The ground term we write as 6S. For D6, the ground term we write as 5D. For D7, the ground term we write as 4F. For D8, the ground term we write as 3F. And for D9, the ground term becomes 2D. Okay, you can pause the videos and check for the different D1 to D9 systems, how the ground term that we write, how we come to that conclusion to become to write the ground term. Okay, therefore, for the Dn ground terms are given, D1 to D6 it is given. So again, we're coming back to that spin-orbital coupling expression that we used to calculate the effective magnetic moment. Mu effective is equal to mu s into 1 minus alpha multiplied by delta divided by lambda divided by delta. Here alpha value becomes 0 if it is a S state. S state means only D5 is here. So D5 is having that S state. Okay, and alpha will become 2 if it is D state. D states are therefore D1, D4, D6 and D9, and alpha value will be 4 for F state. F state means that is D2, D3, then D7 and D8. Okay, then the spin orbital coupling constant lambda, it is the positive quantity. Is a positive quantity for the first row transition metal ion, that is 3D series having the configuration D1 to D5. It becomes negative for the same series with more than half filled, that is D6 to D9 shell. Some of the values calculated or observed are for titanium 3 plus the value is 154, like that for chromium 3 plus it is 91, chromium 2 plus is 57, for iron 2 plus it becomes minus 102, cobalt 3 plus it is minus 125, for copper 2 plus is negative 829. Therefore the lambda value is positive or negative. It can be positive as well as negative. But since alpha and delta are both positive quantities, it is seen that the observed magnetic moment is greater or less than spin only value, as lambda is negative or positive. It is in this way we can explain why the observed moment is lower or higher than the spin only value in several cases. That's what we see in the beginning of this class. The spin only value, it becomes lower or higher compared to the observed value. Okay, so I took the example cobalt 2 with a high spin complex, that is octahedral complex with a strong field ligand. It becomes a high spin complex. It having D7 or it is T2G5 Eg2. Its spin only value is 3.88 only, but observed value is well above. It becomes 4.3 to 5.2. So the observed magnetic moment is higher than the spin only magnetic moment due to the normal orbital contribution is there. In addition to that, spin orbital coupling is also there. That is causing because of the mixing of the first excited state. Okay, from T2G5 Eg2, the first excited state what we write, that is T2G4 Eg3. This one contribute, or this one it along with that of T2G5 Eg2, that mixing of orbitals creates the higher observed magnetic moment. The extent of spin orbital coupling will depend upon the strength of the ligand field. Okay, it also depends upon the nature of the ligand, weak field ligand or strong field ligand. For the low spin octahedral complex, CO2 copper 2 plus complex with high spin values is given, whereas for low spin value, which is having the John Teller distortion, the observed magnetic moment is much closer to spin only moment, since the ground state allows no orbital contribution. So if it is a low spin complex of octahedral complex, then CO2 plus we will write as T2G6 Eg1. This you can cross check in my previous classes, how with low spin complex or based on the ligand, how the electronic configuration is written. So here T2G6, that means in T2G it is completely unpaired, completely paired. Okay, 6 electrons are there. Therefore, there is no orbital contribution. Therefore, spin only value will be almost equal to that of the observed value. Value slightly excess of spin only magnetic moment, spin only magnetic moment orbital contribution of the first excited state is due to the spin orbital coupling. That means if any changes in observed value, that may be due to the spin orbit coupling only. So in case of tetrahedral complex of cobalt 2 plus D7 configuration, electronic configuration we write as E4 T23. There also the observed magnetic moment is higher than that of a spin only value. Okay, so here E4 T23, there is no orbital contribution. But the because the lower energy level E4 it is filled and there is no orbital contribution as such. The observed higher moments are caused by spin orbital coupling only, which allows the mixing of higher levels, say E4 T24 and E4 T24 and 4P1. So that's about the spin orbital coupling and its contribution. Hope you understood the concept. I'll explain with further examples in coming classes. So thank you very much for watching my video and have a nice